Try a quick experiment. Hold your hand out in front of you, give your fingers a little wiggle, and then slowly squeeze them into a fist. Your hand instinctively knows how to use just enough force. When you pick up a raw egg, your brain calculates the weight and the fragility of the shell in an instant. You squeeze hard enough to lift it, but not so hard that it breaks. We adjust this grip hundreds of times a day. We use a power grip to hold a heavy tool, a pinch grip to pick up a single coin, and a precision grip to write with a pen. While this feels effortless to us, translating that biological instinct into math required decades of engineering. For a robot to match that simple squeeze, it has to process thousands of data points about physics and pressure in real time. To build hands that feel, engineers map our anatomy. 27 human bones become a rigid metal skeleton. Biological muscles and tendons are replaced by actuators and steel cables. Finally, nerve endings are mimicked by digital sensors measuring physical force. A robotic hand functions as a part-for-part mechanical mirror of your own anatomy. But the hardware is only one part of the story. Without a way to process information, the hand would still crush every object it tried to pick up. In a feedback loop, fingertip sensors detect contact and send data up the arm. The central processor analyzes this pressure. If it's too high, it commands the motors to loosen the cables. If slipping, to tighten, perfectly stabilizing the fingers. This process is continuous. As long as the robot is holding the item, the sensors keep sending information back to the brain every few milliseconds. This constant conversation between sensors and motors is what allows a machine to mimic the same invisible process your own nervous system uses every second. Applying these biological concepts to machines has changed how we treat injury. This antique prosthetic from the early 20th century relied on heavy leather and simple springs. Today, by using electronic sensors, modern prosthetics allow people to move and hold objects with their own thoughts. In industry, we use larger versions of these grips. While early factory robots like this Unimate had simple metal claws, modern versions use precision sensors to assemble smartphones and electronics at high speeds. In medicine, these grips are scaled down for extreme accuracy. Surgical robots use tiny mechanical fingers to perform delicate operations inside the human body that would be too small for a human hand to reach. NASA even uses massive robotic arms, like this Canadarm in space, to grab and repair satellites where it's too dangerous or difficult for humans to work manually. Despite these advances, the technology is still catching up. A single advanced robotic hand may require over 100 individual sensors just to simulate a small fraction of the feeling you have in your own fingertips. Engineers continue to build more complex machines, but they look to the hand you're using right now as the most effective design nature has produced.